My name is Will Covington, and this is my survey on long short-term memory, or LSTM. My motivation for this survey kind of was founded in an interest in the stock market, like many other people. And through some preliminary research, I found that the LSTM was particularly successful, and I wanted to learn more. So the general task that we're covering here is time series processing. And the difficulty with time series processing is um, modeling temporal dependencies and relationships in the data. And so a good way to describe this is suppose you have two vectors and they're identical, but one is a shifted version of the other. This is a pretty difficult task for a machine to figure out that they're identical, because a small shift can actually create a large distance between the two vectors, even though they're identical. So this task is attacked in kind of two different directions. There's explicit modeling, and the idea of explicit modeling is um, to map the time into an explicit dimension, hence the name. So the idea is, you could use a buffer or a tap delay line, and the drawback, of course, is that there's a fixed input length. So once the model is assigned an input length, a size input vector, it's not able to change. The other idea is implicit modeling. And the idea of implicit modeling is, instead of encoding a dimensional aspect, like in explicit modeling, the model determines contextual dependencies by considering previous and current inputs. And a couple of famous options: current neural networks, RNNs, ARMA, autoregressive moving average, and NARCS models. The biggest issue with recurrent models are vanishing exploding gradients. And vanishing exploding gradients make learning long-term dependencies, typo, very difficult. So recurrent neural networks are kind of the precursor to LSTMs, proposed by Michael Jordan in 1986. And the real big proposition is the state unit idea, where we feed back, and if you can look in this diagram here, you feed back the output unit information into a state unit, which has its own self-recurrent connection, and then that is also fed into the hidden layer. So that means the hidden units are dependent on the current input to the system and the previous output of the system. Recurrent neural networks are trained conventionally with backpropagation through time and RTRL. Backpropagation through time is similar to feed-forward network backpropagation, except if you think about a recurrent network, you can unfold the network in time and make it a feed-forward network. So each feedback connection could be unfolded, and then the initial time would be your start of the network, and feed forward to your current time. And of course, like I mentioned previously, the gradient here vanishes. And the idea is that as the number of time steps pass between important information, so an important input that you want to remember, and a final input, the gradient decays to zero. The idea is, all inputs in between the important information or important input and current input are effectively noise, and they have to be processed through the system because the recurrent nodes, or the hidden units, will have to process the input. So this requires the networks trained for a really long time in order for long-term dependencies to be recognized by the model, which results in a very sensitive model to noise. And the converse case there is, if the model's not trained long enough, the important information from time steps previously will be clobbered by more recent inputs. So this brings about the LSTM, the long short-term memory architecture, introduced by Schmidhuber and Hawkrider in 97. And the idea was to solve this problem of long-term dependencies. The basic idea is there's a memory cell, and that memory cell is this circle with the slash through in the middle here. And it's called the constant error carousel. And the idea is that every time step, the information held within this constant error carousel is multiplied by a weight of 1.0, so an identity, and passed back to itself. So it's saved. And the input, which comes in from the left side here, is controlled by this input gate. And the input gate also receives connections. And the idea is that the input gate connections determine when information should be let into the constant error carousel. And similarly, on the output, there's an output gate who have connections that determine when information is passed from the constant error carousel to the next layer of the network. So I think the best way to think about this is the input and output gates are like soft multiplexers. The gate inputs tell the gate how relevant the information is. The input gate decides how much of the input should be let into the memory, and the output gate decides how much of the memory cell information should be released to the output. And these are various equations assorted with the unit. The LSTM forget gate was introduced by Schmidhuber along with Gers and Cummins 2000. And the idea here is to allow the LSTM unit to handle continuous series data that doesn't have labeled beginnings and ends. So the initial LSTM that I just presented required input sequences to be clearly labeled with a start and an end. And long sequences or continuous sequences, the input and output don't reset the memory cell before the information becomes unbounded. The information stored is unbounded inside the memory cell. And this results in a saturation of the output activation, which essentially causes the gradient to become zero. And it turns the LSTM cell, interestingly, into a typical RNN unit. Causing the gradient to vanish, ends up making the unit unable to distinguish between when it should let information in and out, and it can no longer learn long-term dependencies. So the forget gate was added, and the forget gate controls the reset of information stored inside the memory. So it also has inputs, as you can see, and these inputs are learned. The weights are learned to determine when in a sequence the memory cell should reset itself. And the basic idea is instead of having the 1.0 multiplication inside the constant error carousel, it's replaced by the activation from the forget gate. So at a weight of close to 1, the cell state would keep all the information that it currently had, and a weight close to 0, it would reset. So the people, which is a second edition here, was also introduced by Schmidhuber in Gers 2000. And the idea here is to teach the network, how to act without an indicator. So the previous LCMs required an indicator for when the prediction should take place. So before the forget gate, there was indication of input. Start and end. Now we want to be able to learn, okay, without even how can this model work without even being told when it has to predict? And the real idea is, we want the model itself to be able to count a number of time steps. So the proposition is to introduce these peephole connections, and the peephole connection connects from the inside of the memory cell to the input of the 3 gates. The idea is each gate now, when it's making its decision, gets to see what is at the current time step inside the memory cell. So it knows when a particular memory exists, okay, it's time to release this memory, or it's time to let something else in, it's time to forget, based on what is inside the memory cell. In their study proved that the LSTM memory cell can slightly increment its value and then learn to open the output gate once the memory meets the threshold, which is pretty cool. Figure 4 here shows a comparison of the different LSTM variants, and they're labeled by their no output gate, no forget gate. What's missing from the complete LSTM? As you can see, as you move toward the right here, the performance is getting worse. And there's a couple key takeaways from this study. First is, and it's important to mention that right here, the TIMIT data set is a speech data set, but it was also trained on online handwriting and music prediction. So speech, handwriting, music prediction, these different LSTM models. And in general idea, the removal of the peephole unit doesn't make a significant difference. Removal of output activation or forget gate causes large performance degradation. So they're kind of labeled as the most crucial aspects of the LSTM unit: output activation, forget gate. And the idea there is the two prevent, the output activation prevents memory from growing unbounded. And, as we previously discussed, forget gate prevents the output activation from being saturated. And the last kind of key insight for continuous data, the input gate, output gate, and output activation are really imperative for good performance. So there's a couple other LSTM variants, add-ons I'm going to discuss. Dynamic cortex memory. The DCM is actually pretty cool. The idea is that the LSTM has connections that have to learn the same information, and it just makes training time and convergence much slower. So the idea is, if you make connections between each gate, between the forget input and output gates, they can share information and learn in a collaborative sense. And the DCM here, you can see at the bottom, the idea is, compared to the LSTM, they're trained on a task of, if presented a sequence and a certain index, remember the value at that index until the end of the sequence. And it was trained on similar tasks. There's another that was two inputs or two indexes, remember them, add them, and return them at the end. And the added connections from the DCM, you can see at the bottom here, proved an improvement over the LSTM. And T here is the length of the sequence. So as the sequence increases, the task gets more challenging. Bidirectional LSTM, the idea is to learn forward and backward context. So this is the equivalent of reading a page from left to right and from right to left, and you can gather contexts that are in front of and behind the keyword that you're currently looking at. And I'll discuss a little more of the results of the by LSTM later. And the LSTM encoder decoder, which is a pretty important application and really variant of the LSTM. The encoder decoder structure uses the problem it attempts to solve is that deep neural networks are useful, but they struggle with varying length inputs, because you have to define the length of the input for conventional feed-forward deep neural network. And what was found is you could use an LSTM to process each individual sequence element and use the LSTM to map a length varying input to a fixed length vector, and then use another LSTM to process the fixed length vector to an output. And that'll also be covered in depth as we move on. So training methods, like similar to the recurrent neural network, LSTM uses BPTT and RTRL. Truncated RTLO was presented for the LSTM, and the idea is once errors hit the memory cell, they're cut off, so the errors can't propagate They can propagate eternally or indefinitely within the constant error carousel, but once they leave the constant error carousel, they can't propagate around the network forever. There's a couple other really interesting, and we can go into depth a little more of BPTT. The idea is to assign a certain amount of blame to each weight in the network. Um, and like I mentioned earlier, you can unroll a recurrent network, and the idea of back propagation through time is pretty similar to conventional back propagation for feed-forward network, if you consider the network unrolled. RTRL propagates an activity gradient forward. So the idea is that it's capable of running in real time, or it processes, or as inputs are sequentially processed, the algorithm's capable of changing weights. Evolino is an interesting approach to training, and basically what it does is it adds connections or weights or add units to an LSTM network, and then it evaluates how well that network performs using gradient descent to learn. So it could, maybe it would add an extra weight from the input to a gate, and then evaluate how it learns, and then add, another weight on top of that network, evaluate how it learns. As you can see, it's kind of an impractical algorithm. Its computational complexity is undefined. DEKF LSTM is another method that was presented. The motivation behind this is it's a Kalman filter, but gradient descent algorithms don't typically take into account previous weight changes. They just operate based on gradient and the error at the current time step. So the idea here is to recursively compute the least square solution, and you're taking your past weight changes into account. Proven to have faster learning, converges better accuracy, again, larger computational complexity. Okay, so related models. First related model is ARMA or ARIMA, autoregressive integrated moving average, presented by Box and Jenkins quite a long time ago. Autoregressive is combining dependencies from lagged observations. Moving average is dependencies, another typo, between observations and residual error terms. The integrated aspect is measuring the difference in observation time. Integrated, officially makes the time series stationary. Generally, you consider it, one time step you're integrated. ARIMA is useful for short-term modeling, but is really poor to model nonlinear relationships. And as you can see on the right here, this is a training presented several different models by LSTM, LSTM, and ARIMA based on financial data, evaluated root mean squared error. And as you can see, that the by LSTM is significantly improves over ARIMA and LSTM itself. And you can kind of attribute that to ARIMA not being able to model nonlinear relationships within financial series. And then on the right side here is percent reduction. The second related model is the gated recurrent unit. Gated recurrent unit, it's simpler than the LSTM, has less gates and less connections. So the idea is faster convergence. It has two gates, update and reset. Update controls how the memory is updated, and it's kind of similar to a coupling of the input and forget gates for LSTM. The reset gate is kind of similar to the output gate, but it really acts kind of like the forget gate. So there's two gates that both have a touch on the LSTM forget gate. And the one other real important difference is for the GRU, memory is shown to the output at every single time step. So the LSTM, the memory is only shown to the output when the output gate is open. But here it's shown at every time step. And it's an important connection. Going back, I talked about which LSTM aspects were the most important. And we decided that the output activation and forget gates were the most important. And the GRU kind of combines these functionalities. So it's still a successful unit and has similar to performance to the LSTM without having output or input gates. On the right side here, training on music and Ubisoft data sets. The metric here is negative log probabilities, and the as you can see, that the GRU is kind of primary advantage, although not a ton difference between the three. And the last related model that I'm really going to touch on here, although there are many more, is the transformer. And the transformer conventionally is not a recurrent network, but it was presented as an alternative to the LSTM encoder decoder. And the idea is the problem with the LSTM encoder decoder is that while the LSTM can map a varying length input to a fixed length vector, it tends to map a lot of unimportant information. So it maps a lot of noise and doesn't focus entirely on what important inputs there are. So the attention mechanism was developed to solve this problem, to tell the model what needs to be focused on. And then the transformer combines the idea of attention with kind of encoding decoding structure using self-attention. The advantage of the transformer as compared to the LSTM encoder decoder is that it converges faster. It's more capable of parallel processing because it doesn't sequentially read in each data point. On the right here, you can see the transformer architecture, and then it's kind of confusing looking data, but the general idea is that the transformer and the LSTM have pretty similar performance. And this is on a LibreSpeech data set. But of course, to highlight here, the transformer is more computationally efficient. Takes less time to train. So now we're going to get into applications. And so I'm only going to cover a handful of applications in this presentation, but there are plenty of applications with the LSTM. First, natural language processing. You can go straight down the list of different NLP applications for LSTM. And the real idea is that LSTM is great at determining context between inputs. And so with context, a language is full of context, so the LSTM is pretty great model. Frequent LSTM architectures, bi-LSTM, LSTM encoder decoder, LSTM combined with convolutional neural network, and of course, like I mentioned earlier, LSTM with attention. And another important point here is the blue up top is a comparison of a couple different LSTM based models, an attention mechanism model there, and it's judged on the blue BLEU metric. And the blue metric is bilingual evaluation understudy. It computes a geometric mean. And then right below that is another kind of comparison of different models, several of which are LSTM, bidirectional LSTM here. And this is the Stanford sentiment tree bank metric. And this is an important kind of point to make. The different metrics, they're not quite as, for these complex and translational tasks and natural language processing tasks, they're not as straightforward as just accuracy for a bitwise operation or a vector operation. So it's kind of an interesting research point. The models are judged, but it's tough to tell explicitly what the metric means. Second application, video and image processing. The LSTM is used for various video and image processing tasks as well. Image caption generation, human behavioral analysis, body pose labeling. And a lot of these are combinations of multiple models, CNN, attention, and LSTM, of course. The interesting thing to pay attention to here is the body pose labeling here in this um, figure 11b. Now this is percent accuracy, and ERD is the encoder decoder structure that I mentioned earlier. But it turned out that these processing images, um, the best model that's been shown is LSTM with 3 layers. So the encoder decoder structure used a CNN, LSTM, and a feed forward neural network, but the multi-layer LSTM works the best. Finally, applications, forecasting. So stock market prediction, how I kind of got interested in this, and energy load forecasting. Both of these, interestingly enough, were trained just with LSTMs, LSTM units. For stock market prediction, interesting conclusion. If you look in the graph here, the top right, this blue and green is the predicted, and it's pretty close, but I believe the accuracy turned out in the mid 50% range, and the kind of presented feedback is, the stock model has to take in other factors into account, like the news or kind of day-to-day understanding, other than just previous stock market data. Energy load forecasting, other kind of interesting conclusion. The LSTM has a pretty strong advantage on forecasting individual use, but when individual use was aggregated together, temporal dependencies were kind of averaged out. So those dependencies for energy use were, people wake up at a particular time, they brew coffee, they do certain things on holidays, and with large numbers of people, that's averaged out, and the LSTM is worse performance. A couple other applications: handwriting recognition, speech, music processing, mentioned briefly before. Robot controlled and program execution were 2 kind of outliers that I thought were interesting, so I wanted to include in here. In conclusion, finally, the LSTM, capable of long-term dependencies, and follow up to the recurrent neural network. LSTM cells control when information is stored, released, and forgot based on the input, output, and forget gates. The cons, as I mentioned, there's a lot of weights with the LSTM. So redundant information is often learned, which was proven by the dynamic cortex memory and the gated recurrent unit. And also, the recurrent nature kind of prevents parallel processing as opposed to the transformer. It's difficult to gauge recurrent neural network, which includes LSTM performance on many tasks, which I mentioned with the blue and SST metrics. So with more time, I think I'd like to focus this project more toward, or maybe further toward, how these different models perform based on metrics, and how the metrics themselves impact the direction of research. Are the metrics really useful, or are they just benchmark hacking? And of course, if you're interested in seeing the sources for this, you can reach out to me. Thanks.